start. So thanks again to everyone who joined today. I will be talking about our experience with neural net verification, and of course I'll be talking from declarative programming perspective, seeing it as PADL. The results that you're going to see today are the results of a grant we won long ago. We promised two things in this grant. First promise was to make an honest investigation how type theory and types can help with neural net verification, whatever the conclusion is. And the second promise was to engage with real people, because, of course, from the funder's perspective, anyone who does type theory is not a real person. And so you needed to promise to engage with AI people, machine learning people, and security people. So those were the two promises, that we do an honest investigation of types applicable in this area, and plus honestly engage with real users. So today I will just tell you what happened so after we promised that and got the money. Isaac turned out to be quite a big grant because of that promise of engagement. But on the programming language side, the three faces and names that you see are the main contributors: Matthew Daggett, Ben Koke, and Bob Atke. So much of the results that you're going to see today, thanks to them or with them. There are other programming language experts such as Catherine Stark and Rob Stewart there, and some PhD students, but PhD students were mainly with machine learning backgrounds. And Luke Arnaboldi is a security expert. There's quite a big team that was working on this. So let's try to go for the first topic. So what did we find out in terms of usability of types and more generally declarative languages in this area? So for the purpose of this talk, we will be, let me just try to remove this. We'll be talking of a neural network as a function. You usually see these interesting pictures, but really it's just a graphical representation of sums and multiplications within the network. So usually you have a vector as an input, vector as an output, and whenever you see a connection, it means that a vector element is multiplied by whatever weight you have in the connection, and every so-called neuron is really just summing up the incoming weights. I'm saying this because yesterday in the panel discussion, we couldn't even agree exactly what we're talking about, right? Some people are saying we'll be talking about implementation of neural networks, abstraction of neural networks, probability theory behind neural networks. And here we'll be talking about functions and how to verify a function of this type. For sometimes it won't even matter that this neural network was obtained by training, and sometimes it will. So in some parts of the talk, it will be extremely important to understand that this neural network was not written by a human, it doesn't really have a semantics. All these different weights that are hidden from us were obtained by optimizing those weights based on the input and output examples, as it happens in neural nets. So that at some point will become important. But for a lot of this work, we'll just be looking at a black box function from vectors of reals to vectors of reals. Okay, so why neural networks? They are ideal for tasks where the semantics of the domain is poorly understood. That's why people use them. So no wonder we struggle with semantics of neural networks. It's because people only use them when they don't know the semantics of the subject. They can learn to approximate complex functions. They're tolerant to noisy and incomplete data. However, their solutions are, of course, not easily explainable, and they're prone to a range of bugs and safety and security problems. That is, for example, you can easily fool a neural network by disturbing one pixel in an image or something like that, which can be safety and security threat. So the first question one would be honestly asking him or herself when you start a project of this kind is, can we verify properties of neural network enhanced software? And I suggest we just go and break down this question in many ways. There are a few words, and we'll just go for every word in that question because there is something to say almost about any word there. So you will see at the top of my slide that question reiterated several times, and I will be highlighting the exact aspect of that question that we'll be considering at the moment. So can we verify properties of neural network software? So if you attended yesterday's panel discussion, towards the end of it, people were saying, what are the properties? Can we define the properties? So the question number one is, can you even state a property that you want to verify? So what kind of properties there are? First of all, there are universal properties, that is, properties that you want to hold for any network. An example of this property was actually suggested by machine learning community way back in 2014, when they said, we really hate it when you have an image, say on the left, it's 97.6% confidence that it's a red light. You add a little bit of perturbation, get an image that to a human looks exactly the same. Suddenly, neural network has 81% of confidence that it's green. So the problem was flagged by machine learning community that this is something we definitely don't want to happen. And if you do verify something, please verify that this doesn't happen. And the bad thing also that these attacks, that's why they're called adversarial attacks, they're imperceptible to human eye. So that's why sometimes people talk about them in security terms. Attacks transfer from one neural network to another. So if I can fool my neural network, I can attack yours. And they affect any domain. So it's not only imaging. Whenever you apply neural network, you can craft these attacks. This property can actually be very easily specified. It's not a big deal. So it turned out to be, from the logical perspective, it's very easy property to state. So informally, what we want to say is that small changes in the input should produce small changes in the output. So if it's a little perturbation, you shouldn't change dramatically the decision of the neural network. And remember, we just defined the neural network as a function from vectors of reals to vectors of reals. With this, it's very, very easy to massage down this informal property, as I've written, into a formal property. So what you're really saying is that you're going for, you're given a data set usually, you get some x hat in your data set, and then you define a property that I want for all vectors that are only within a small distance from the image in my data set. The distance is bound by some epsilon to result in a situation when I apply the neural network to my image, I apply a neural network to any of those images within the epsilon distance, and the output of the neural network compared between these three images, my ideal image and my perturbed image, should be less than delta. So mathematically, it's very easy property. Let's just make sure that everyone, absolutely everyone, is happy with it, because we need to have one example that you should have in your head as I proceed with the slides. Okay, everyone buys this, and everyone agrees it's kind of easy. It's good. Okay, so that was good. Well, one problem you can see with this, of course, why people might find it unsatisfactory. This is only for one image in my data set. And then I can, of course, go for all images in my data set. But if I implement autonomous car, it may or may not encounter anything that looks like my data set. So it's a very local set of inputs that we are verifying. That's the main weakness of this method, because mathematically it's fine, but practically it's not particularly applicable. Second source of properties for us is this. Sometimes neural networks are used to approximate standard algorithms. And why? It's mainly for performance reasons. So you had a standard algorithm, then you throw it away, train a neural network to do the same thing, but you still want to have some guarantees about behavior of your neural networks, in which case verification properties are derived from the properties of your original algorithm. So let's have a look at the example. So this is a hello world example of neural net verification. In 2017, Guy Katz and his co-authors discovered this example. There's ACOS-XU, collision avoidance system, that is actually in use in the United States. In simplified terms, what you have is you have your own chip, you can measure an angle, speed, you have intruder speed, intruder's angle, and distance between you two. And based on these parameters, you, in your own chip, should make a decision whether you turn left, turn right, or declare clear of conflict and you proceed. So these are those different parameters that you've got, and outputs. Strong left, weak right, strong right. Okay, so originally this problem was implemented as a lookup table. So this is your classical algorithm, whichever you wanted to use. And it was used for many, many years. It was quite large. It was 2 GB lookup table. And then if you want to implement this on a drone and a small aircraft, you say, well, I don't want to have 2 GB given to this, so why don't we train a neural network? to essentially compress this 2 GB table into a small network. And so you can derive properties of the neural network that you get this way from the original lookup table. And in the original problem, there were 10 different domain-specific properties. And I'll only give you an example because it's not so important for this talk, but just as by means of an example. So AKS property 3, if the intruder is directly ahead and is moving towards the ownership, the score of clear of conflict will not be minimal. And then you get essentially first-order formula suitable for an SMT solver to crunch. And this is the technology that was used initially to resolve these problems, essentially SMT solver plus some heuristics to deal with neural nets. I suggest we're not going to read this carefully if the main idea is clear. It's basically first-order logic that you crunch with a technique that's similar to SMT solving. And then there can be more properties, we think, which are much less explored. And they're domain-specific. Well, an example, I know you're trying to model a fluid in a tube. And maybe you want to prove that the energy is conserved or something like this. This is really something that's under-researched and underdeveloped, but would be immensely useful for people who use neural nets in engineering. So majority of cases when I see people coming to me, it would be engineers who say, we have this neural network, it models some physical process, what can we prove about it? Anyway, we know something about properties. It's not like we completely don't know anything about properties that we can verify. So let's put that box and start filling in the picture. Challenges we have in that domain. From theory point of view, finding appropriate verification properties is hard. And in general, the problem of missing specification for neural networks is not really resolved. So we have some information about some of the properties, but it's not like for any neural network, I know exactly what I want to verify. And a lot has to be done to even understand the general properties we already know. So when we started this work, we realized that in machine learning community, there are several definitions of robustness. And some of them overlap, some of them contradict each other. And then people optimize for different definitions of robustness and verify different definitions of robustness. So sometimes we even just spend on understanding different definitions of robustness, how you encode them, how you train for them and verify. There's also a lot has to be done on programming domain-specific properties like AKS-XOO in a clear way. So what we found, there are plenty of bugs in the software related to the fact that the engineer stated what the aircraft should do in what we call problem space, in the language that the engineer knows, which is velocity, distance, angles. A neural network then crunched some normalized inputs, which were no longer velocity and angles. There were some normalized real numbers, say in the interval between -1 and 1. And when people state properties that the engineer wanted in the language of a neural network, there are lots of errors creep up in there. So at the very least, programming languages could help to specify the properties in a clear way. And I'm referring to a recent paper that we're submitting shortly as a tool paper. And throughout this talk, we'll be talking a lot about this second point of how programming languages can help to specify the properties of neural nets. I will be doing this color coding for you, so please watch the slides. When you see that something is underlined and with a star, it will mean that I think that this is a place where declarative programming is particularly useful. Yeah, so for example, I'm not understand the general properties or finding a missing spec because I'm thinking it's partly machine learning problem. So we need to talk with people who know machine learning and actually find out what it is that they want us to specify. But some problems of which I mentioned are clearly programming languages. Like you wouldn't come with this second problem to your machine learning expert and say, could you build for us better programming languages? So watch out, I will be highlighting the things. And you can, by the way, disagree and raise your hand and say, no, I think this is programming language problem. But this is my judgment as to which of them is really sort of like an iconic application of declarative programming. Okay, so we come back to this question at the top. Can we verify properties of neural networks? Suppose I'm happy with the property I stated. Suppose it's robustness. And then, okay, so what sort of verification algorithms already exist on the market? And we found out, even 4 years ago when we started the project, that plenty of domain-specific verifiers existed, and since then a lot more appeared, or those that existed back then became better. So there is Marabou from Guy Katz and his team. That's the team that first introduced the ACOS-GZO example. They're really the pioneers, and this verifier still goes strongly. It's SMT-based. There's Iran and others similar based on abstract interpretation. There is VeriSig, alpha beta crown based on interval arithmetic, linear bound propagation, etc. There are international standards and competitions developed in this domain, and if you want to have a look, you can. But for the purpose of us, the important bit was that all of these different provers, they agreed on a format in which they write properties, and which is called VNN-lib. If people here know SMT-lib, it's very similar to SMT-lib, but a little bit adapted to neural networks. So at least we found some standard language which this community understands, which was very useful. Okay, so we proceed with drawing a picture. We have a property, and we found some tools that can actually crunch some of those properties. That's good. What challenges we found on the verification side? A big challenge is undecidability of nonlinear real arithmetic. You want to reason about real numbers. You don't have decidable algorithms to do this automatically. The next issue we found was scalability of neural network verifiers, and the community is very active for working on that. And of course, whenever you use SMT technology or similar, there will be a question of ultimate correctness of the algorithm that you use for crunching those neural networks and generating proof certificates showing soundness of those algorithms. Was, again, one of the problems we found. So let's have a look at the color coding here. Well, I'm putting this question mark now, star in the question mark. Well, undecidability of nonlinear arithmetic itself is probably not the problem of declarative programming. It's what it is. It's not decidable. But I'm still signing it as a star, because even if you have undecidable nonlinear real arithmetic, you can, for example, generate better error messages. So you give a query, it falls outside the fragment you can process, and then through type system or otherwise, you can inform the user and say, by the way, you're out of linear fragment in that particular line, in that particular specification. And so this paper here in CPP last year was about using types in order to report to the user when his or her query about a neural network goes outside of the decidable fragment. A scalability of neural net verifiers is not the issue for types, but if you think that SMT solving itself is also declarative language, then it's bang on what that community is worrying about. And proof certificates is a classical thing that you would look for if you're working on declarative languages. So a lot in this domain is actually something where declarative languages could be very useful. Okay, let's crunch our question in a second, in a third way. And how about neural networks? Let's actually remember that those functions that we're verifying are neural nets. So before we verify a neural network, how we even know that it satisfies the property we want to verify? So it simply very often fails that your property goes through the verifier, or your verifier says, nope, it doesn't hold. And a good thing would be to retrain your neural network so that it does satisfy the property that you want to prove. So very often it goes like this: your verification attempt fails, and then you say, well, I need to do something about my neural network. You retrain it, and then hopefully you will be successful in verifying a retrained neural network. Okay, so challenges on the machine learning side. First of all is to understand and integrate property-driven training. Well, first of all, what we found, and was very useful already 4 years ago, there was already starting to appear work about what's called differentiable logics. Differentiable logics are a way to compile down logical syntax into the language of loss functions. And this gives you a generic way to retrain neural nets. So Natalia, my student here, is writing her PhD about that. that was interesting. The question that wasn't resolved and is not fully yet resolved is how to deal with universal quantifiers. So those differentiable logics that we found, they deal with propositional languages, and quantifiers are actually quite tricky. So if that is our robustness property, you'd wonder what your loss function would do with the quantifier. And the general solution, the general intuition is because loss functions usually penalize neural networks. So the training of neural networks goes by penalty, essentially. Loss function gives you the error rate, and then you retrain the weights. So actually, when you want to train a neural network to satisfy a property that's universally quantified, you simply need to find the worst example in this domain of for all x and penalize the neural network for wrongly classifying that worst example within the quantifier domain. And this is what we have been working. So let's have a look very briefly at color coding. So it's just one star for differentiable logics because there is something to do in terms of declarative languages, but part of this is machine learning perspective. And for quantifiers, I put question mark because a lot of this, when you say, well, it's search for worst perturbation in this real space, in this quantifier domain, it really gets very much in the way of what standard machine learning does for adversarial examples. So much of this is machine learning rather than declarative languages. So, so that's the story. Actually, it's not just the training, but it's PGD and the GSM attacks known in machine learning that also need to be at work there if you want to have universal formulas as your properties. All right. So we're almost towards the end of the stop question there. The question was, can we verify properties of neural network enhanced software? So from the very start, we were not interested in neural network sitting on its own in a vacuum. We were interested in the whole infrastructure that embeds the neural network. And so to these three questions, we add the fourth. How do we verify complex systems that contain neural nets? So in reality, this picture, very few people are interested in just having this picture on their computer. Most people are interested to have this additional block when after you're happy with your neural network, you integrate your knowledge, your verification of that neural network into verification of a large system. Okay, so what kind of challenges exist in complex systems? Well, it largely and very often intersects with the area of cyber-physical systems because that's when people really, so for example, I have a controller, we'll have in a second an example. I'll have a controller which is executed by a neural network, and then I want to show that the overall car, overall robot doesn't collide. It's really not so well understood. So from time to time, like in the previous year in CAV and RV, there were a few talks by NASA Boeing researchers trying to do something about these complex systems that have neural nets. And in our opinion, declarative programming may probably unlock some of the problems here. And we will see shortly an example that hopefully will prove the point. In fact, maybe that will be the most useful application of declarative languages in this domain. Okay, so just to summarize, we found 4 very big challenges in this area. And some of them are strongly a declarative language problem like number 2, and some of them kind of declarative language problem plus. So the 4th one is really declarative programming problem, but number 1 and number 3 is kind of, it's a mix, it's a hybrid problem between machine learning and declarative programming. And I want to add the 5th question to the mix. How to hold and implement all these components soundly. Because you have one thing, the other thing, it looks very messy. And you would think, okay, I think probably declarative programming can help, strongly help here in just having a system in which all of these components interact in some kind of safely and orderly way. So let's have a look at this complex system, which we think is particularly promising. Suppose you have a purely symbolic program S, and you have in it some unknown functions. So let's think that this unknown function recognizes images or recognizes intruders. This is where we want neural network to act. And we are now building towards having this neural network. So we have an embedding function from P to real vectors. And we have an unembedding function from real vectors to R, so that we could somehow relate our neural net to the ideal black box function that we're trying to model. So we're thinking that our neural net, f from Rm to Rm, somehow approximates the ideal control or whatever your h is. And so, yeah, if you compose them, you basically should more or less have an h. And your complete hybrid program would look like this. So you have your standard software, and you have your neural network with embedding and unembedding parts. So if you wanted to prove that the overall system satisfies some desired property psi, you're essentially down to these three blocks. So let's have a look at the block at the bottom. Well, you want psi to hold of sh. And you want to have a property that you say, well, if some property phi holds of h, then the overall property of phi is holding of sh. Right? So if I can prove something on the neural network side, I can guarantee that the overall system is all right. So if neural net's safe, the overall system is safe. This is a very natural property to want. And well, question to you, just to wake you up a little bit. Do you think we have provers already on the market that would be all right with number 3? What would be your favorite prover to prove this? Suppose I'm giving you already a proof that the neural network is behaving fine, and I'm asking you to prove that the overall system is behaving fine. Yeah.
Yeah, I think there was a paper a couple of years ago where they had like a system that did this using abstract interpretation, combined it with a program where they had an embedded neural network. But so they had a framework, but it wasn't a completely generalizable system.
Okay. Well, what language would you use to prove number 3? Well, would you use an SMT solver to do this? Would you use Isabelle Hall? Would you use Koch? Would you use Agda? What would you use for number 3? Well, let's think. So this is probably high order because it will be talking about functions. So you probably don't want to use first order solver like SMT solver. You probably want to go to Isabelle Hall, Koch, or Agda, somewhere where you could reason about functions. Okay, so number 1 is also easy, right? So this is just proving the property of my neural network in neural networks terms. And this is exactly what we're talking about. All those neural net verifiers, they do exactly number 1. And what we found is that number 2 was missing. There was no tool 4 years ago or now that would fill the gap between the two. And mind that if I'm using ITP here, Coco or Isabel or whatever, tools that are applicable to number 3 usually not very good at crunching neural networks in raw format. And the other way around, tools that can crunch neural networks in raw format are not very good at proving functional properties. And so I cannot apply tools I use here in 3 and the other way around. You need to have some gluing layer between them. And basically you need a tool in which you're going to be showing that, well, if I can prove a property of a raw neural network, I can also prove some other property of that network embedded into my problem space. And this is the gap that we're trying to build in this project. Is this all right? So this is kind of important. So let's have a look once again at this picture, because it will clarify what's going on actually. We have a problem space. So think about your engineer who knows how the aircraft should behave, who knows how the robot should behave. And think about your neural network living here. So in the problem space, you have your specification of the overall system and the big safety property. You also have specification of your embedding and unembedding functions to neural nets. So these are your velocity, speed, distance. And these are just vectors of real numbers normalized between 0 and 1, or whatever you want to normalize it into. So you train a neural network in terms of normalized real vectors, and you verify the neural network in terms of normalized real vectors. But what you want to prove is something completely different. You want to prove something about speed of your robot, and it will never collide. So there is a big embedding gap between the two. And when I'm saying we're building this middle layer, we're essentially building a tool that would be able to talk to all these components. So you write specification and the engineer gave you with velocities, distances, and you compile it down to train, to verify, or to integrate with your high order language. So that's the essence of that layer that we're building. And overall, that was called language vehicle. It's a domain-specific language on top of Haskell that we built. So you can state a property of neural network in engineer's terms. You will get informative error messages. For example, you could be in the wrong fragment of arithmetic. And then it will be compiled down to either training, verification, or integration with higher order provers. And so this very much fits into our five big questions that we asked. How to hold and implement all these different components soundly together. Okay, so this was a general setup, the problems we found. And now let's have a look at examples. We have a little bit of time. So before we go anywhere else, are there any questions about this picture? Are we all kind of okay? So for the rest of this presentation, I just want to go into examples and show you how this works. Let's take the problem. That's exactly the problem, the kind of problems we think declarative languages community should look into. This is a big system. Well, big, it's quite a small example. But imagine you can extend this later to model autonomous vehicles, robots, or drones. Well, let's try to understand this one on its own terms. It's taken, by the way, from Boyer, Green, and Moore 1990 paper. So the example is not particularly novel. But here you are. So you have a vehicle that moves on x-axis, but you're interested somehow in its velocity on the y-axis. You have a sensor in the vehicle that can determine its position, but the sensor is a little bit noisy, as it happens in life, so there is noise there. There is also wind speed that distorts your car's behavior somewhat. There is a controller in this car, the neural network, that estimates position of the car with some noise and gives you an advice how you should change your y velocity. And the overall purpose is that your car never leaves the road areas. Okay? All right. So in any favorite language of your choice, you can probably program something of this kind. This is an Agda, but it doesn't have to be Agda. Well, let's have a look. What's important for us in this example is to see that we really want to have some kind of high-order language to talk about this overall, the system overall. So you want to define a state that is defined by wind speed, position, velocity, and sensor value. You want to say what observation is. Well, it consists of wind shift and sensor error. And you have your neural network controller that takes previous state, current state, and gives you the advice what to do next. And then, in pretty much standard way, not very different from what Boyer and Moore have done in ACL2 in 1990, you can define next state and the final state. I know, let's poke somewhere in an interesting part of that definition. For example, in the new velocity is computed as your current velocity plus whatever your controller tells you to do based on the new sensor and the sensor reading. And the new sensor, as you can see, is computed as new position plus the error. So you're putting all your errors, all your sensor information in one spec in order to trace how this behaves as a big system. Are we happy with that? I mean, it's a nice spec. It's almost all that you need actually to specify that little example. And now the main safety property. The main safety property would look something like this. If the wind speed never shifts more than 1 per unit time and the sensor is never off by more than 0.25, then the car will never leave the road. Again, this is 1990 formulation of a safety property. This is nothing new. Now this line in Agda, not all of the definitions are given now, but imagine this main theorem can be quite easily written in Agda. So would be written down at the end in something like all valid observations excess imply that your final state will be on road. Crucial for us in this example is that we cannot prove this main theorem without having some guarantees about what the neural network controller does. And the lemma that actually is needed for this theorem to go through is this controller safety. And it boils down to some numbers. Well, let's have a look at this. So controller safety tells us if X is within 3.25 margin, Y is in the same margin, then the controller, you apply controller to X and Y, add 2 multiplied by X, subtract Y, and that should be in less than 1.25. Don't worry about the actual physics, so just trust that the physics works. But this would be the property that you want to be proving. And it's very inconvenient to prove that property in Agda, especially that if you remember that this controller is 20,000 parameter huge neural network. So crunching this with interactive theorem prover, this lemma, is inconvenient to say the least. It's probably impossible to do this for any real life example. Okay, so what do we do? Well, we have just stated number 3, so let's just try to interpret this example back in what we've just said. We've just come to stating in Agda, we could do it in Coq or Isabel, this high-level property. So it's clear that we got stuck with actually proving this property, right? So we were saying we want some property of the controller to imply for us that main theorem. So our main theorem was psi, and we got stuck on this property phi. Well, it's clear that we need to go one level up and talk about the property phi of our neural network, which was controller safety. And we said that we were a little bit stuck for the tool. That's where our vehicle comes into place. I now realize that it might be a little bit too small for the audience, so what I will do, I will just exit presentation mode and start zooming in. So vehicle is the language we've written, and it is for stating properties of a neural network in engineer's terms rather than in neural network terms. So let's have a look. If I go and zoom, I really wanted to have all spec in one slide so that you could see that it's not very threatening either. It's kind of, you can't fit it on one page if you really want it. Okay, so that's our vehicle example. And let me go for, is that all right? Is it readable? Okay, so let's have a look at it line by line. You state the property of a neural network. In our case, neural network, remember, was taking 2 inputs, previous state and current state, and was outputting the advice what to do with velocity, how to change velocity. So we just state that. We have 2 inputs to the neural network, and that's the type of its input. It's the vector of size 2, and we have vector of size 1 as an output. The network next that you see is called controller. It's from the type input to type output that we've defined. This language has this at sign, and this is for integrating all external tools. Whenever you see at, it means that it will pass this information to somewhere, to Python, to verifier. There will be some communication. And you can see that we don't define network here, as a matter of fact. So it will have to refer to the definition of the network that we compiled with Python. We don't define network in this language. This is important. So this is something that didn't exist in machine learning verification before. We clearly state all the methods how we normalize the input. In particular, for this particular controller, this is a normalization function. And this is important to state up front, because what we found in the literature, lots of bugs were coming from people never stating how they actually normalize the inputs to give them to neural net. Well, and then I've just defined safe input and safe output, which is not different from the spec that we've already seen. So current position and previous position should always be in the range minus 325 to 325, and the output should also correspond to the formula we've just seen in mathematical notation. And that's basically it. So you have the main property that says for all x, safe input implies safe output. And that's really all there is. When you see at property, it will again mean that vehicle, this DSL, will not prove this property itself. It will pass it to neural network verifier. Is everyone reasonably happy with this? Okay. So that's all spec, and this gives us this gluing layer between low-level crunching of neural nets and the high-order prover. Well, that's very little left. We have 3, 2, we just need to go and prove the property of the neural network on real vectors. So what happens here is you have a type checker. You've just seen vehicle specification. It's a Haskell-like language, Haskell DSL. What you need to pass all those properties for Marabou, which is essentially an SMT solver, is using type checker that will normalize your query written in vehicle and pass it down to the language of Marabou. Well, vehicle is more expressive than SMT solving language. And those verifiers have different constraints. It should be linear specification, it should have non-alternating quantifiers, because those people who implemented languages like Marabou care about decidability. So what do you do with vehicle specification then? Well, we wanted to have this picture. As a matter of fact, type checking would need to take care of linearity of arithmetic, and if your fragment goes outside, it will give you an error message, and type checking will also need to check your quantifier fragment of your query, and will give you an error message if it goes outside. But suppose my query was fine, and my query was actually fine. It passed all these checks for the correct fragment of real arithmetic. What the compiler does underneath, it will compile the specification we've just seen in nice high-level syntax into something like this. So query 1 and query 2, which is in VNN lib format. So when we found this area 4 years ago, everyone was writing specifications in this format. As you can see, this is very difficult to understand what's going on. For example, all inputs were normalized. So you no longer see, all those speeds, velocities, angles. You see some raw numbers that only neural net can understand. And this dirty work has been done for us. So the user of vehicle would not see this, right? You would see this high-level specification. This will be crunched down for you and passed to Marabou. All right. So we have now covered all three. Essentially, we outsource number one to existing solvers. We do our own spec and higher order language, and we use vehicle to glue the two together. But we haven't covered learning, right? We were saying that you need to train a neural network. And in particular, in this embedding gap, we have covered 1, 2, 3, but we didn't cover training. So what do we do? Well, you may as well use type checker once you've written it. You say, well, now I have this vehicle specification. I can also compile it to a loss function. If I could compile it to Marabou specification, surely I can compile it to a loss function, and then I pass it to TensorFlow. The advantage of doing this is that I'm compiling exactly the same spec in vehicle for learning and for verification, which couldn't have happened without having this high-order language to hold this all together. Just to show you how low level it is, this will be the loss function that corresponds to the vehicle spec that we have just seen. Again, you don't want to write this by hand. And vehicle exists exactly so that you don't have to write this down by hand. But this basically crunches the logical formulas into some function that will compute a penalty for the neural network if it doesn't satisfy the property we stated. And it also uses quantifiers, compiles down quantifiers into the sampling domain, which you sample the worst example that fails your property. Well, this is not to be read by human. In fact, so it's not read or written by human. Your interaction with vehicle would more or less consist of saying, listen, there is this controller spec in vehicle, and I'm interested in controller safety property. Could you choose differentiable logic such and such? And then compile it down to a loss function and use it in training like this. So this is Python code that simply calls vehicle to generate this loss function that we've seen and use it for training. And finally, Agda backend. You can also convert vehicle property into the Agda code so that that bit about the controller that you need to program in Agda is given to you automatically. But this is the easiest part because vehicle syntax is so similar to Agda's. So this was great. I mean, this gives us modularity of code. This gives us reusable specifications, and it uses dependent types for catching specification errors. This is ideal contribution that declarative languages can give to this domain, or so we think. Okay, so to conclude, we have seen challenges in this area, and we've seen that they don't necessarily come from declarative languages or from semantics. There is a theory of neural nets where you need to talk about what kind of properties you want to hold. There are a few problems on the verification side that SMT solving and similar communities are trying to solve. There are problems on machine learning side. There are problems on complex system engineering. All of these are there. But the point of this talk is that declarative languages make a difference for progress in each, or at least I try to illustrate to you that if you come with some interesting techniques from declarative languages, you can make a difference to progress in these four. And therefore, in my opinion, the fifth challenge that you need to add to this list is programming challenge in finding the right languages to support these developments that happen kind of without declarative programming. And this would be the declarative programming contribution to say these are correct languages for you to use if you wanted to make faster progress with the other ones. I like this picture. It's what we thought Vehicle would be when we started the project 4 years ago. It's messy and it's quite big. So it's not easy, right? So we're saying, oh, declarative languages can solve the problem. It's not easy. But I think without declarative languages, holding this together is even harder. So if you like, this could be a mission of a declarative language to put this all in order. Although we didn't create Vehicle for teaching, we actually do use it for teaching for postgraduate students, and PhD students use it for smaller projects. So there was a Vehicle tutorial presented at CAV. We had summer school ICFP. Plans are to try it in PhD training and perhaps develop materials for postgraduate courses on safe AI. So big hopes that it will also be useful for teaching machine learning students. And we're hoping for many applications, so we'll look quite a few. So once you actually have the language, once you have the infrastructure, you then can apply it to neural networks used in a variety of domains: NLP, security, airborne, robots, and engineering. So this is all ongoing work. And this is all I have to say. Thanks for your attention.
Thank you for the talk. Very hot topic, and we have a lot of time for questions. Yes.
Hi. Thanks for the talk. I've got a PhD student working on neural network verification, so I'm definitely going to link him to the video to have a look at afterwards. So one question or thought I had was, in this example where you had the car driving along the road and you're worried about the wind, part of what you were doing there to get the verification of the whole system was you had to have a model of the physics of the car driving on the road, and you also had to have a model of the road, although the assumption was that it was a straight, infinite road. Mm-hmm. So I guess thinking about if one day people want to apply this sort of approach to actual cars on actual roads, they're going to have a model of actual car physics and actual roads. And in terms of actual roads, it's not reasonable to expect an autonomous car to drive perfectly on any road you might imagine. But the people who design roads, I'm sure they have a set of rules about what sort of speed limits are appropriate in what kinds of situations. And some of that knowledge might be written down and some of it might be informal. So I wondered if you had any idea of how declarative languages might help us to get that body of knowledge and put it in a form where we could apply it to a verification system like this.
Well, our main claim here was that if you go in this route rather than specifying it as we saw in Marabou directly in raw vector input vectors, that at least allows you to, well, first of all, this is extendable. So if your knowledge of physics improves, you can clearly specify everything you've got here. Secondly, if you had this controller, which is your neural network, is of course quite a crude thing. It doesn't know about physics. It works on these normalized vectors. It's quite a stupid thing. So very often, your properties about this controller will boil down to something quite low level. But at least it does help that when you go to the vehicle specification later, you state all your assumptions about this. Remember, we said we now can declare a normalization function, we can declare all of this. So you at least have a trace, because very often we found there are bugs because someone implemented neural network, trained it for some funny conditions. How this relates to large system is never specified, never documented. So at the very least, programming languages can give you the right language in which to document this stuff. So if a new engineer comes, they can observe what happened, what was normalization, what were the bounds.
Thank you.
Well, thanks for a very nice talk. I wanted to go back to the ACAS XU example you mentioned at the beginning. It's a great example. But if I remember correctly, there were 3 ACAS systems. So one was the neural network, one was the huge table you mentioned, the 2 gigabytes table. And then there's the original model, which is just trigonometric. You know, it's just computing the point where the 2 planes will be closest and basing decisions over that. I think this first algorithm, which involves lots of trigonometry and real arithmetic, so it's a little bit tricky, but it was formally verified in PVS, I guess, by Munoz and Dovek. And so my question is, in your opinion, which form is most useful as a specification for verifying the neural network? Is this a huge table that is already pre-computed and then linear interpolations, or is this the complicated trigonometric formula?
Okay. That's a very good question. Well, we didn't think in these ways because we're always thinking that we don't have any choice. So I work with a few companies, and there what happens, they had, so for example, one company is building oil rigs, and they need to estimate whether certain substances, oil or whatever, is in liquid, gas, or solid form. And they have full physics describing the matter, but they say, well, to implement it there in the place, it just takes too long to compute all those differential equations, it takes too much energy, so let's replace it with neural nets. So they don't ask themselves whether that's a good thing to do, they just do it. But then of course they say, well, but the whole rig will blow up if that neural network is mistaken, so how can we prove it? So we were going mainly that, we don't have a choice, many people on this planet start substituting exact mathematical computations with neural nets, and what we can do is to just put boundaries on those neural nets and say it will never go beyond that boundary on the output if you put boundary on the input. But as you mentioned, what's easier for verification? I don't know, maybe it is easier to verify a neural network because the property you are verifying is much more simple. It's in a way stupid compared. If it was the whole mathematical modeling of the system, then you go in Coq and do the whole formula in Agda and go for full formalization of mathematical properties. It's a huge library that will correspond to all those physical processes. And to verify a neural network, you just load an SMT solver and you crunch it. Of course, it's at the expense of getting a very simple property, perhaps opaque property even verified, right? You only say for these input regions, I guarantee output regions. But if you were just worrying about simplicity, accessibility for, you have a bunch of engineers who could just crunch it to SMT solver and do it, perhaps it is easier to verify a neural network. If you think that this simple property you get verified is sufficient guarantee for you of the safety of the system. Yeah, because even with the vehicle, and what happens if it's outside of the boundaries? So we had this controller. Always with neural net verification, the main trouble comes actually at applicability of this stuff. So if I go back more quickly to maybe it was a mistake, I should have just exited. So this is our controller. I suppose I'm happy with this. I verified this and I've proven my safety property. But what if current measurements are just not within those bounds? So should I shut down the system? What do I do? Because this neural network does not know anything apart from this property, or as a verificationist, I only proven this. So this is a disadvantage of using neural nets instead of full physical modeling of the system, because neural network becomes opaque, it doesn't know things, then as a verificationist, you know very little. And so if you are within the bounds, you're in your comfort zone. If you're outside of these bounds, you don't have tools to really reason outside of the verified bounds. But this, I guess, is not... We were trying to solve the problem, right? To make this, to put order into what the practice that already exists. So again, is it a declarative programming language? I don't know. It's probably an engineer problem, how they prefer to model their physical processes. So it's not our recipe to do it. It's more like we're trying to clarify what they do already, or make it nicer, make it safer, what they do already.
Questions? Time? Then I have one. I'm not sure whether it was in. I think with these neural networks and so on, somehow you always have the trouble between somehow the accuracy and the performance, which often is amazing, and explainability, yeah, with the decision trees and so on, you don't get this. Exactness, it's understandable, and always this trade-off. Is there something like this here as well, that if you want to have something verified, that you need to say, okay, I have to scale down to some extent what I allow?
Yeah, in machine learning, they talk about trade-off between accuracy and robustness, for example. So, for example, it's easy to explain. This controller was trained from data. The data knew nothing about the desirable property. So the data, it was just trained to be accurate for the data as given, and the data may actually even violate the property. So if you fail to verify this, and may happen, then you pass these properties through differentiable logic, through a loss function, and retrain your neural network to satisfy this property. Well, if your network starts satisfying the property, but your data wasn't, you become inaccurate on your data set. So there is always this trade-off, but if you really care about the property, you don't care that your neural network excludes some of the examples. It becomes less accurate as long as it becomes safer. So there is this trade-off between faithfulness to the data and faithfulness to your property, and you may actually choose to be faithful to the property rather than the data. And this, by the way, in a way, provides explainability for the neural network that you trained.
Could I, remove the data could I remove the data that does not, for example, satisfy the preconditions?
Yeah, but if you remove the data, then you don't need neural networks. Then you're back to square one.
I mean, only train it within the safe bounds.
Yeah. I mean, you can first pre-train on data, then retrain this again. We didn't look that closely at the practical aspects of exactly when it should be triggered. We noticed that machine learning community wants to be able to train with the property, and we implemented this as functionality. But there are more works on machine learning side, and people actually study what's the influence of training with properties as opposed to training for data.
Perfect. Let's thank the speaker again for this exciting
Thanks for your
talk.
attention.